Hey everyone! Have you ever stopped to think about how a computer could actually understand language? I don't just mean recognizing words, but really getting the deep structure, the logic, the meaning behind a sentence. Well, today, we're diving into a really powerful framework designed to do exactly that. All right, so here's our game plan. We're going to start with the big challenge of modeling language itself. Then we'll get into the really unique two-level architecture that makes abstract categorial grammars, or ACGs, so special. After that, we'll see how they work in the real world, how they handle all the tricky little details, and we'll wrap it all up with why this stuff is so important. So, first things first, the problem itself. Let's face it, human language is messy, it's fluid, it's packed with nuance. Trying to create a strict mathematical model for something like that, well, that's one of the biggest challenges in both computer science and linguistics. And that really brings us to the core question, doesn't it? It's not enough to just parse words in a line. A computer needs to figure out the grammar, the logical connections, and the actual intended meaning, all at the same time. How on earth do you build a system that can juggle both syntax and semantics so elegantly?
Well, one of the most powerful answers comes from the world of logic and advanced computer science. It's called Abstract Categorial Grammar. Think of it as a super sophisticated framework that's built from the ground up to model not just the surface of a sentence, but its deep underlying structure and meaning in one unified system.
So, how do ACGs actually pull this off? Well, the secret sauce really is in their architecture. They don't just operate on one level. They have this really clever two-level system.
And this is where it gets really interesting. ACGs split the problem in two. You've got the abstract world, what they call the teto grammar. Just think of this as the pure logical blueprint for a sentence. And then you have the object world, the pheno grammar, which is the actual concrete thing we see or hear, the string of words.
And here's how that journey from blueprint to reality actually works. You start with an abstract term, a pure structure. Then, this special mathematical function, a homomorphism, acts like a translator. It takes that abstract blueprint and interprets it, turning it into a tangible object term. And that object can be a string of words for the syntax or a logical formula for the meaning.
You can see how this two-level design makes ACGs incredibly flexible, almost like a Swiss Army knife for grammar. It can work like traditional grammars, where syntax is king and dictates the meaning, or it can treat syntax and semantics as equal partners. It's so versatile, in fact, you can use it as a kind of universal framework to encode and compare totally different grammatical systems.
Okay, that's the theory. But what does all this elegant math actually let us do in the real world? This isn't just a beautiful idea on a whiteboard, it has some serious computational muscle.
And this right here, this is a huge deal if you're a computer scientist. For a really important class of these grammars, the second-order ones, which is what second refers to, we have a critical guarantee. We can actually prove whether or not a sentence belongs to the language. That means the system is predictable, it's reliable, and you can build things with it that you can trust.
Now, if we dig into the nitty-gritty, the practical versions that you'd actually use, called lexicalized ACGs, are what's known as NP-complete. Now, that might sound scary, but it's actually good news. It means they belong to a class of problems that, while hard, are very well understood. We have strategies to tackle them, which is essential for building real-world software.
And believe me, that theoretical power isn't just for show. It translates into some seriously impressive practical tools. We're talking parsers that can handle huge chunks of a real language like French, systems that can generate natural-sounding text, and models that can handle really tricky stuff like adverbs, the passive voice, and even figuring out who did what in a complex question.
Let's take something really tricky, like anaphora. That's just a fancy word for when a pronoun like he or it refers back to something you mentioned earlier. ACGs can use some pretty advanced tools to track these references across an entire conversation, building up a coherent picture of who's who and what's what, kind of like how our own brains do.
Okay, but we all know language isn't just about big structures. It's the little details that matter, right? Things like verb endings and grammatical gender. So how can ACGs handle that super fine-grained level of detail?
This is a classic headache for anyone trying to model language. Think about how in a language like Spanish, an adjective has to match the noun's gender. The red car is el coche rojo, but the red house is la casa roja. Enforcing those kinds of agreement rules can be really tough with a basic grammar.
So what's the fix? Well, the solution is brilliant. You integrate something called feature structures. You can just think of these as little digital tags that you attach to words. They carry extra info, like number plural or gender feminine. By adding these into the ACG system, the grammar can now check these tags and make sure all the agreement rules are followed, making it way more powerful and accurate.
All right, we've gone deep into the weeds here, from abstract theory to the nuts and bolts details. Let's pull back for a second and focus on the big picture. Why does any of this really matter?
So, what's the big takeaway here? ACGs are way more than just another grammar theory. They're this incredibly elegant system that finally connects sentence structure with actual meaning. That design makes them a powerful Rosetta Stone for comparing other grammars, but they're also robust enough to build practical AI tools that can handle the amazing complexity of real human language.
And that brings us to one last really mind-bending question. The way we use language is so deeply connected to how we think, how we reason, how we experience the world. So, if we could one day build a truly perfect mathematical model of language, one that captures every last bit of its structure and meaning, would we be taking a giant leap toward creating a truly conscious AI? It's a fascinating thought, isn't it?